Hello everyone. This video will act as a tutorial for the Neuromorphic Makers Kit, and specifically the binary to decimal application. So inside of the software repository for the Neuromorphic Makers Kit, there is a set of files that are dedicated to this application, a spiking neural network and input files, output files, things like that dedicated to it. But to start out this video, we'll start with a hardware setup. So I'll start out with how to set up this circuit such that we can set up this binary to decimal application. And so the circuit for the binary to decimal application is pretty simple. It's just three buttons that we're going to connect to the input of the Neuromorphic Makers kit here. And then the output is very simple as well. It'll be a blinking LED built into the output Raspberry Pi Pico here, so there's nothing to wire up for that part. So really, for the hardware part of this, all we're going to do is we're just going to wire up on a breadboard. See my breadboard here. Um, the input side, these three buttons, into the Neuromorphic Makers kit. And it's be pretty simple. All you need for the hardware for this entire application is, of course, you need your Neuromorphic Makers kits. You need a power supply for it. For this one, we've just chosen the simple like AC to DC adapter here, connected to our barrel jack. That because the Makers kit has a nice barrel jack on it. And you need to load and code onto your Raspberry Pi Picos for the kit. You need a micro USB. See the connector there, micro USB cable to connect to your computer, so that way you can load code onto these. Um, like I said, I have my breadboard here, and then here I have 8 jumper cables, breadboard jumper cables, and then here I have 3 uh, 10 kilo ohm. The exact resistance here doesn't matter. Just a little bit on the higher resistance side is nice. So 10 kilo ohm resistors. I just need 3 of them. And then here I have 3 buttons. These happen to be 4-pin like push buttons that you get with a bunch of like Arduino kits. As you can see there, all 4 pins. But this is essentially like a 2 pin buttons built in. So you can use a 2-pin button here and follow along just as easily. And really for this, I'll be treating this 4-pin button almost as if it is a 2-pin button in the first place. So it should be nice and easy to follow along with. Okay, let's go ahead and start setting things up. So we won't need the kit for the actual kit here for a little bit, so I'll just put it off to the side. And really here we'll focus on the breadboard. If you've never used a breadboard before, it's pretty simple. It's really just a simple way of wiring things together and without needing to do anything like soldering electrical connections or anything like that. And so if you've never used a breadboard before, you can see it's basically a grid of holes, and some of these holes are electrically connected. That is, they're essentially wires underneath on the facade of the breadboard here on the inside that are connecting them together. And specifically, what is connected together is each row is electrically connected together. So if you put an electrical component on 2 different rows, they will not be electrically connected together, but two things on the same row will be electrically connected together. So it's as if you just have a wire running beneath the 2 things that you have on your breadboard. And notice there's a big gap in between here. That runs down the length of the breadboard. That breaks up the electrical connections. So I say each row is connected. Well, it's more like each half row is connected. So if you can see where I'm pointing here, this row that I'm sort of highlighting within this resistor is all electrically connected together, and on the other side, this row that I'm pointing within into the resistor is also electrically connected. But this row is not electrically connected to this row because of the long bridge in the middle of the breadboard that is splitting up, breaking up that connection, insulating that connection, I guess you could say. But yeah, that's really all you need to know about breadboards, and just makes it really nice, as you'll see here in a moment, to wire things together and fit them all in a nice little grid without needing to solder anything or use any other sort of like board or design your own PCB printed circuit board or anything for your little embedded system here. Okay, go ahead and to start off, we'll just go ahead and throw in our 3 push buttons. So you can really put them anywhere you want on the breadboard here. All that really matters is that you make sure that you get all of the pins of the button nice and solidly inserted into the breadboard. That's 3. Okay, and then Yep, just double checking that we have it solidly in. And from here, we need to define a ground. So this will be our logical zero, right? Because it'll be a zero voltage essentially. That is our common ground in our electrical circuit. And nice part here is we can wire all the buttons to one ground that will share a ground on our neuromorphic makers kit. So all we need to do for that is we can choose sort of arbitrarily one side of the button from any one corner of the button um, just to be ground. And then, like I said, we'll all wire them up to the same ground. So I actually just need um, I can sort of put the wire wherever I want here, but for the sake of spacing things out nicely, I'll decide to put my ground wire here, just in between two of these buttons. And now what we need to do is we need to have our power going to the buttons. So the Neuromorphic Makers Kit, Raspberry Pi Pico specifically on them, they use 3.3 volt signals on the GPIO pins, so the pins that we're going to use for our buttons. And so what that means is that we need to make sure that the input signals from these buttons, it'll have a 3.3 volt input going into the Makers Kit. And what's really nice here is that the Makers Kit has a port that has an output 3.3 volts on it. It has a few of them actually, supplied by the Raspberry Pi Pico microcontrollers, and so we get to use that. But similarly to ground, for now we'll just put a wire that's going to be like a placeholder of where we're planning to actually connect that. And so I'll just put it exactly on the opposite side of ground. And also notice here I'm doing a little bit of color coding with my wires. Jumper wires are normally come in like a bunch of various colors, but in general I do like making black ground at the very least, or some shade of red or orange. My high voltage, VDD, whatever you want to call it, power supply, anything like that. And yes, I do have other orange wires, but this is just what I have. So I'm just loosely following the guidelines here. Okay, so now we have these placeholders. We actually want to get these signals to our buttons. We want our buttons be able to be connected to our electrical ground, and we want our buttons to be able to be connected to our logical high, which is, like I said, VDD, the power supply, the 3.3 volts. And to do that, we're going to use some of the other wires here. And okay, so I'll start off here. I'll start off with my little tiny wire here, I guess. Doesn't matter exact lengths. It is nice if you can try and find wires that do fit where you're going to route them pretty well, so that way you're not using a bunch of extra wiring and just sort of ends up as like a tangled mess all over the place. But once again, you work with what you have. Okay, we'll start off here. I'll take one wire, and I will go to one arbitrary side of my button, whatever looks convenient, most convenient to me. And then, once again, like I said, with the breadboard, a row is all electrically connected together. So since I just put the end of this wire here, this wire that I just placed, in the same end is where we're going to be connecting our 3.3 volt power supply for the buttons, like the input 3.3 volts for each button. That means that this wire here is going to be at 3.3 volts level at all times. And that means this side of the button here is going to be at 3.3 volt level at all times, which is what we want. And then likewise, we'll connect. I'm going to use the same corner, same side of my button here for all of my 3.3 volts power supply sides of the button here. So for each button, I'm still using the same corner, same side. It's all going to be connected to logical high, 3.3 volts, VDD, whatever you want to call it. And so, yeah, here we already have a good portion of our wiring done here. And basically what we've done is, since all of these are connected together. I guess to make it simpler, I'll connect this one here. We have this one side which is connected to our 3.3 volts, as I've mentioned, and then all on one row, we've connected 3 more wires. Each of those wires is going to the same side or one corner uh, of a different button. And so what that means is, since inside the breadboard all of these wires are electrically connected together, all of these wires will always be at 3.3 volt level, and they'll always be at a digital high level, digital 1, digital high, whatever you want to call it, VDD, um, at that level. And so that means you plug in this into 3.3 volts, uh, everything on this side of each button is going to be at 3.3 volts. And so what this will allow us to do is, whenever we press each button, each one individually, we want that to essentially connect to our input port of the Neuromorphic Makers Kit for the input ports, one input port for each button. And as we press that corresponding button, it'll connect that input port to a logical high. It'll connect it to a logical 1, a digital 1, 3.3 volts VDD. And so now we need to go ahead and connect the other side of the button to ground. So that way, whenever you're not pressing the button, that same port, that same input port, will be connected to a logical 0. So whenever the button's not pressed, it'll be a logical 0, and whenever the button is pressed, it'll be a logical 1. This is called positive logic, I believe. So to connect these, we're not going to be using jumper wires. We'll actually be wanting to use these resistors. And the reason we're using resistors is basically because whenever the button is pressed, we want it to be connected. We want the basically we want the electrical path of least resistance to be on the side that is connected to the positive 3.3 volts rather than ground. We want it to be connected to ground whenever the button's not pressed, but whenever we press the button, we want the path of least resistance to no longer be the to ground, but instead be from the positive 3.3 volts into the button. So that way it basically, the 3.3 volts overcomes the ground signal. The logical 1 overcomes the 0. And if you have an electrical connection of where you have your input port and it's connected to a 3.3 volt port and also connected to a ground port, that is going to electrically short that system there, which of course you don't want. It can potentially harm your whatever your device you're connecting to, but it's basically left floating somewhere in between that ground to 3.3 volts, and that will absolutely mess up the system you're trying to wire here. And so what that means is that you can just use a resistor that's connecting in between your ports that you're on your Neuromorphic Makers Kit and the ground side of things, the 0 volts. And what that allows you to do is that will then make, whenever you have this button pressed, now that it will be the path of least resistance to be connected to the positive 3.3 volts, because now you have this resistor that provides electrical resistance between the ports that you're connecting this to on the Neuromorphic Makers Kit and ground. So whenever the button's not pressed, the Neuromorphic Makers Kit is not connected. The Neuromorphic Makers Kit port is not connected to the positive 3.3 volts at all. It'll just be connected to this resistor, which leads to ground. And because then the path of least resistance is to ground, the signal there will be a logical 0, which is exactly what we want. So yeah, we're going to take one leg of the resistor and put it on the opposite side of our positive 3.3 volts. And then we're going to take the other side of the resistor and put it on the same row as our ground wire here. And then we're going to do the same thing for each of the buttons and all 3 resistors. So I'm taking my second resistor here, put it on the opposite side as the opposite side as the 3.3 volt side, and then I'm going to connect it the other side to that same row as the ground wire. I need to move this one over. There we go. Same thing, opposite side as from the 3.3 volts on this button, all the way over. Let's see if we can reach here. Oh, it might not. I might have to move these over so that way it can reach. Okay, I got that one shaped here. Sometimes with these like little through hole resistor things, it helps to take the ends and try to shape them a little bit before you put them in the breadboard. Breadboards can be a little bit finicky. Okay. So let me get the end here. There we go. And then how far can this actually reach? It looks like I'm going to get here. There we go. Yeah, I'm going to end up having to move this wire over just a couple of holes, just so that way everything can actually reach to it. I need my resistors to be able to reach over to the other side there. Okay. Here we go. And here what we want to do is we do want to make sure that any legs of these resistors, because the legs of the resistors are conductors, of course, so you want to make sure that none of the legs of the resistor touch the opposite side. So basically what that means is anything connected to this ground wire on the breadboard, you don't want to touch the opposite side of the resistor, because then that will just short that resistor completely, and then the resistor won't do what we want it to do, which is ensure we have a safe path between our neuromorphic makers kit ports and ground and 3.3 volts when the button is pressed. Okay, last thing we need to do to set up all the rest of our wires here with these last three wires is these will be the wires that will just be simply connected into the ports of the neuromorphic makers kit. So you want to put them on the same side as the resistors before they actually go over into the ground part. So you basically just want to put it on the same electrical node as the resistor for each one. So that's what I'm going to do, is the same row where I put my resistor on the opposite side of the button as the 3.3 volts. I'm going to put my input wire there. I'll call these the input wires because they will be our input ports to the neuromorphic makers kit. Okay, so here's the actual neuromorphic makers kit. Actually, I'll do a quick close-up here of what I have. So as you can see, this is what I have. Um, this right here is the ground wire that we started off with, and as you can see, what's connected to that are the ends of each resistor, and then the ends of each resistor on the opposite side, they each go to the opposite side of the button as the 3.3 volts. And that's the same for each resistor. And then on that same node, electrical node, is connected in that same row of the breadboard are connected the input wires. And so you'll notice it's the same for each of these three buttons. And then on the opposite side of each button, you'll see all these wires are connected all to one node, which is this node right here. That is one row of the breadboard that's all electrically connected together. And then this wire will be our 3.3 volts, so go on 3.3 volt side. So all that's left to do is to plug it to the input ports, the neuromorphic makers kit, and you'll see the neuromorphic makers kit is labeled. So anything that I say here is absolutely labeled. So you want to make sure you're on the spike encoder side. So you'll see here where it's labeled spike encoder because that will be our input side. And want to make sure that I have all of these things connected to the right spot. And so anything, whenever I say GP0, GP1, it's labeled right here what I'm connecting it to. And there's the 3.3 volt out that we'll be using as well. So anytime I say anything like that, I'm referencing these labels right here and the corresponding port that goes into. Okay, so I'm going to take the I'll have it oriented the way I had it earlier. So now I'm going to take my ground wire and put it into a port labeled GND, which is right at the top left of the neuromorphic maker skit. And now I'm going to take my 3 input wires for each button. It doesn't really matter which one goes to which. You'll sort of figure out once you get the app loaded on here in software which button does what. But they need to be connected ports GP20, GP21, and lastly GP26. And those will be our 3 input wires. And it does help to go in order from top to bottom, so that way you're at least is sequential on which one does what and which button represents which binary of the bit of the 3 bits. It makes the most sense for the most significant bit to either be furthest away from you or closest to you without alternating between bit significance in between. That's just a little confusing. Okay. And then lastly, oh, it looks like one of my wires came unplugged here. Fix that really quickly. This is one of the worser jumper cables I've used before. Lastly, I'm going to connect my, oh wow, this jumper cable is really loose. That's bad. Okay, lastly, I'm going to connect my, let me fix that, hopefully for the last time here. There we go, that's a better one. Okay, and lastly, this is just my 3.3 volts input that will power the positive side of all the buttons. And I will connect it to the one labeled 3v3 underscore out. It can be any 3v3 underscore out, but I'll choose to put on the spike encoder since all of this will be connected to the spike encoder nicely. Yep, this is the basic wiring. The only other wiring we'll be doing is plugging the computer into each Pico one at a time, like I'll show you here in just a minute. And then the DC, the AC to DC power adapter here into the barrel jack to actually power the kit power supply. Just for the sake of completion here, I'll show you what that looks like. Plugged it in, and it's that simple. Okay, so that's it for the hardware portion of this video. Okay, now on to the software portion of the binary to decimal application for the Neuromorphic Makers Kit. So for the software for the Neuromorphic Makers Kit, as you can see on the right here, I have open in Bitbucket the embedded neuromorphic repository. This repository is the Neuromorphic Makers Kit repository. The actual repo was created before it got its name as the Neuromorphic Makers Kit, so that's why it's not just labeled Neuromorphic Makers Kit. But you will see in the main README that this code is for the Neuromorphic Makers Kit. So see, it's all about the kit. There's an image of the kit PCB with all the Raspberry Pi Picos on it, block diagram, bunch of good stuff in the README here. But for this video, I'll just show you how to get started with the with getting all of the prerequisites software set up with a nice little script that I have in this repository. And we'll start with that and then go into how to build everything for the binary to decimal application, and so that way we can get it loaded onto our Neuromorphic Makers Kit and get it running. Yep. Okay, so without further ado, I will be doing this on Ubuntu 22. This is my personal laptop machine that I'm actually doing this on. I'm going to be connecting the Raspberry Pi Pico microcontrollers too, so that way I can load code onto them. But to actually use all of the software tools, all of the software, all the kit software will not be running on this machine. It'll be running on a remote machine at the University of Tennessee, Knoxville, one of the Hydra machines there, which runs Red Hat Enterprises. And the kit software is, of course, compatible with all Linux operating systems that I know of right now. But it's also compatible with all Unix-based operating systems, so you can run this on macOS as well. Currently, we do not support Windows, though. So if you do have a Windows machine as your personal machine and want to get started with this, I definitely recommend getting some sort of like remote access to some Linux or Unix machine, or loading Linux onto your personal machine, which isn't too hard as well. So that's what I recommend for that. Okay, and so like I said, I'm going to be SSHing this machine, so I'm already connected to the VPN the university requires us to use to connect to these remote machines. And so I'll go ahead and go to my existing TENNLab repository here. And one nice thing, and the reason I'm actually doing this on this remote machine is we do not have sudo access on the machine. Any students do not. And so because of that, this is allows me to show you that the script I have to set up all the dependencies for this software, you don't need sudo access at all, which is absolutely fantastic. And lots of times it's very difficult to get software set up when you don't have that required sudo access for your computer. But you don't need that, which is fantastic. So as you can see on the right here, I'm going to go ahead and just clone over um, the embedded neuromorphic repository. This does assume I do already have on this remote machine an SSH key set up that links to my Bitbucket account. And you will, for the setup script I'll show you in a little bit, you will need the same thing to GitHub. So you need GitHub and Bitbucket and have a SSH key on the machine that you're doing the software stuff with linked to both of those accounts. So that is one prerequisite. And to go over any other prerequisites for this software, it's really just you need like GCC, G++ support for compiling C code, C++ code. You need that, and then you need like really other basic stuff to run this setup script I'll show you in a minute, like which is just curl and really simple commands that your Unix space machine will likely already have ready to go. Okay, so I'll clone this in. And you can clone this wherever you want, which is fantastic on your machine. And so we'll just wait for this to complete here. All right, that's done. So now I can cd into that repository. So now we're in the repository. I'll clear. This is the embedded neuromorphic repository. This is the neuromorphic makers kit repository. And to be able to use this stuff, we really need to have some dependencies. And to install them, it's really all about getting the stuff that we need for the Raspberry Pi Pico microcontrollers, so that way we can compile code for those microcontrollers and load them onto that microcontroller, onto the microcontrollers. That's what the main dependencies here are all about. So not anything too complicated or out there. And what's very nice is, as you can see, I LS the repository here, is we have this script, this bash script that I've written recently, which is the setup dependencies linux.sh script. And I don't know off the top of my head if this will work on Mac OS, which is why I labeled it Linux, just because I'm confident it'll work on Linux systems. And so take that with a grain of salt. You might be able to use this for Mac OS. It might take a little bit of editing. If not, you can go into, as you can see in the documentation on the right of the screen here, you can go into the usage section, requirement sections, and I do have a link here for setting up the Raspberry Pi Pico on Mac OS, which I have used before and gotten it working. So that shouldn't be too bad. And so that also means that you do not have to use this setup script at all. If you want, you can install these things independently or use your own existing copies of any of the stuff you may have on your machine. I just wanted a quick and easy way for new users that don't have these prerequisite software libraries to just get set up so that way you can start using the kit. Let's go ahead and check out this script so that way you can see what it does. And for prerequisites for the embedded neuromorphic repository, the neuromorphic makers kit software, all you really need are three things. Number one is, as you can see in the top here, is you need the Raspberry Pi Pico SDK. And that's why I mentioned before, you will need a GitHub account and have your machine have an SSH key linked to that account. So that way you can clone something from GitHub. And what you're cloning is the Raspberry Pi Pico software development kit. And that's just code that you can run on the microcontrollers on the Raspberry Pi Pico. And that code is a dependency of software in the Neuromorphic Makers Kit. And so that's thing number one. Thing number two is the ARM GNU toolchain. This just allows you to compile code for the this just allows you to compile C plus code for the microcontrollers on the Raspberry Pi Picos. Those microcontrollers have some ARM CPU cores on them, and so because of that, you need this ARM tool chain so that way you can compile code for those CPU cores. And then the last thing that you need is the TENNLab framework, and you need it to be set as you need it set in this FR environment variable, the directory to that TENNLab framework. If you have your own copy of the framework, your own clone of the framework, you don't need to use this one. So if you run this script, you can go ahead and kill this copy and just set that FR environment variable to wherever you have your own copy of the framework. That's completely up to you. Sometimes it is nice having a spare copy that you're not really messing with as well. So that's whatever you want there. And just to reiterate, you definitely do not need to use this script. It's just a quick and easy thing to get set up and running. If you don't want to set this environment variable for the neuromorphic framework, that is optional. The only place it's used is inside of a make file inside of the app compile directory that I just highlighted up here. So if you go into app compile and go to the only make file there, you can change this and you can find this framework directory and set that to whatever you need for your own personal machine if you don't really feel like using this environment variable. So I figure that's worth pointing out. Okay, and so now we'll just go ahead and run this script. So I'll chmod u plus x, the name of the script, so that way I can make it executable on my machine, and then I'm just do /setup, and yep, it'll start blasting away. This will take a few minutes, so now you can get up, use the bathroom, take a stretch, grab some coffee. Yep, so I'll just let this run. Okay, that script is done running to set up all our kit dependencies. So now that that's done, I will note that that actually creates a directory in home, and the directory is called Neuromorphic MakerSkit, as you can see in up here in this part of the script I forgot to mention before I started running this. So if you want this to go anywhere else, go through this script and find and replace Neuromorphic MakerSkit with whatever directory you want relative to home, or if you want, you can even make it go somewhere not in your home directory. So yeah, and so that's where it puts all of these dependencies is in home/neuromorphic MakerSkit. So I'll go ahead and cd to it and show it off here. As I mentioned, the three different things: the framework, this GCC toolchain for compiling for ARM CPUs, and lastly the Raspberry Pi Pico software development kit. Those are the three things. It's almost all set up. The last thing is that it does, as I mentioned earlier, it sets some environment variables and also adds something to your path as well. So because of that, you need to source.zshrc. And by the way, if you're using a shell that is not ZSH, like the default is for the University of Tennessee Knoxville Hydra machines like this one, then you will also want to go ahead and change that in the script as well, because it does put that stuff, as I'm highlighting right now, in that .zsh. So if you're using bash, for example, you'll want to put this in .bashrc and just do a find and replace with zsh for bash. But I need to source it because so that way it actually does set the environment variables that I want, add the thing to path that I want. And alternatively, you can just log out and log back into your machine. But I'll just source it here. And I'll echo out everything that it sets. So here's the Raspberry Pi Pico SDK path, that environment variable. See, it's just the path to the repository that it cloned. Same thing for the neuromorphic framework. That FR environment variable that I mentioned before, just the path that to the newly cloned TENNLab Neuromorphic framework. And lastly, like I said, it just adds something to your path as well, and I won't show that for the sake of time here. Okay, so all of this is set up. And yes, it did create this directory, but you don't actually have to do anything now in this directory because everything's been sourced to environment variables added to your path. You can just leave this alone if you want. You don't have to do anything else with this directory. And that means you can go back to wherever you desired to clone your embedded neuromorphic repository for the kit code. And so for me, that was TENNLab embedded neuromorphic. And now I'm ready to roll. So I'm going to go ahead and go into the app compile folder here, And what I'm doing with AppCompile is a C++ program that generates C code that's going to be run on these Raspberry Pi Pico microcontrollers that make up the kit. And the way it does that is you just feed it a TENNLab JSON file that represents a spiking neural network. It's an array of spike encoders and its array of spike decoders, which are very common, and especially with say Eon's trained applications and Eon's trained spiking neural networks. It's all going to be one JSON file, which that is going to be true for this binary to decimal app. So it's all a single file of JSON that represents all of the stuff that we're going to load on the Neuromorphic Makers kit. And this app compile program just reads in that file and also reads in some user code of what to do with the inputs and what to do with the outputs, which is all the user has to write as part of the Neuromorphic Makers kit. And it'll read in those three things, and then it will output compiled binaries for the Raspberry Pi Picos, one for each of the three Raspberry Pi Picos. So then you can just take those three binaries and load them onto your Raspberry Pi Pico microcontrollers, which I'll show. But for now, we'll just go ahead and make this C++ app because there is a make file, and then you make like any other C++ app. I guess I'll clear to make everything look good first. But yeah, make clean just to be safe, and then make all. This shouldn't take too long. A lot of the time is that this is a newly cloned TENNLab Neuromorphic framework, which has a decent amount of code in it. So it will take just a second for the code in that neuromorphic framework to compile. But the actual app itself is very fast. So yeah, that, pretty much all this was the framework. But now the last thing was just this app compile app, and we're good to go. So now I'm good to run it. So put it in bin. So see, there's the executable. So all I need to run is bin/app compile. And then I'll go ahead and do it this way, and I won't give it any arguments, but you'll notice here are all the options and arguments that you need. Um, and so usage, you'll notice that it requires the very least this dash dash JSON option, which is this one right here. And it really needs the JSON that you're actually going to convert into C code to run on the Raspberry Pi Picos. And so all we really need for this app that we're doing here is this JSON observations and actions options. And so I'll be abbreviating them as I write them out: -j, -o, -a. But the idea is that once again, the top one is just this is a spiking neural network we're going to run on the kit, and the associated spike encoding mechanism and spike decoding mechanism, all in one JSON file. And then the dash dash observations, that's going to be the user written code for binary decimal app. It's already been written, but it's just some user written code, two simple functions, a setup and like a loop function, similar to how the Arduino library works if you've ever used that before. And those user functions are just there to basically read in button input on the observation side and send them to the spike encoding mechanism and send them into the neuromorphic system and send them into the neuromorphic makers kit. And the reason that's user written is so that way the user can attach whatever sensor or thing they want to plug into the kit that they want, and they can customize that and write their own code for it as they see fit. And then lastly, the actions option, that is sort of the same thing, but on the other side of things. So you're taking the output from the spike decoder that's been encoded into some sort of action from your spiking neural network. And this is my essentially output number that I'm going to use in some way for this application. And binary decimal, that's very simple. Observations going in are just binary numbers from 3 different bits on 3 different buttons. And then the actions on the outside, that's very simple as well. It's a number from 0 to 7, 8 total numbers to the power of 3 that represent the decimal equivalent of the input binary number. And that's going to be how many times the output LED on the spike decoder blinks, is that number of times. It's how the actions get used in the, once again, user written, already written for the binary and decimal application portion of this kit app. Okay, so that's just a little bit on the app compile program. If you want more information, please consult the readme.md file inside of the software repo. This one that I've opened on the right. And there's an entire section on app compile. Sweet. Okay, and so I've already made this, and so I'm ready to run bin slash app compile and dash J, and where it's at is in dot dot slash networks slash RISP. We're using the RISP neural processor in this example, and then it's just called binary decimal. And once again, this has all the stuff that we need in it. It has the spike encoding mechanism, the spike decoding mechanism, and the entire spiking neural network inside of this one JSON file. And now all that's left are the user code that is the user code that I mentioned earlier. And so we're going to do the dash observations, and then where that's at is it's in spike encoding, spike encoder, excuse me, slash observation source. This is where we have some pre-written observation source files. And once again, binary to decimal. And then action, similar thing, spike decoder, action source, binary to decimal. That's it. We run it, and it's got to go through and so the Raspberry Pi Pico SDK wants you to use CMake. So this project does use CMake. That is something that is set up here as part of the project. And because of that, it is running CMake, and that's what's doing all the compilation outputs that you see right here. But all the CMake list.txt files, all that stuff is already set up for you inside the repo. So we got to wait just a minute. This, by the way, on some subsequent compilations, this will be much faster as well because it's not having to do all of the setup that you see right now, which is very nice. Okay, now that that's done running, that took just a minute to compile everything. It actually generated the C code in way less than a second, and all of that rest of that time was just CMake doing its thing to actually compile all those source files for the Pico microcontrollers. As I said, first time run that takes quite a bit longer than other times, but took just a minute, definitely shorter than running the setup script earlier. Okay, so what this gave us is, as I mentioned, our output binary files that we can just load directly on the Picos now. Everything has been set up. All we have to do is essentially drag and drop these binary files on the microcontrollers now, and it's ready to roll. And so just for the sake of things, I will show where those are at. So ls, I'm still in app compile, so I do need to do dot dot slash, and spike encoder. It goes to the build directory, and is going to be a U of 2 file. So see, here's our first binary that we'll be loading onto the spike encoder Raspberry Pi Pico, the Neuromorphic Makers kit. As you can see, label here, spike encoder.uf2. Very nice. And then the same thing, but for the spike decoder. And then the same thing, but it is going to be processors slash RISP. We will not be using Ravens, the other currently supported option in the Neuromorphic Makers kit right now. And there's our binary for that one. So these are 3 binaries. These are the only files we need from this entire app compile process. And so with that, I'm going to exit actually, just to make things easy, I'll just make a new tab. And now I'm just going to SCP those files over. So I'm just going to SCP my address here, Hydra 23, and I have to remember where it's at. I believe it's TENNLab slash embedded neuromorphic slash I'll start with the first one, spike encoder, and then it's in build, and then it was capitalized, I think, on this one. I'm not too consistent with that, but that's all right. And then I'm just going to throw it in downloads for now. Okay, let's see if this works. Only reason it wouldn't is if I have my file path wrong. That looks good. Okay, and so now I got to replace encoder for decoder in 2 spots there. Same thing. And then lastly, it is in processors slash RISP. And I think this one's lowercase because I was not quite consistent with the naming of that. That's all right. There it is. And so now if I ls my downloads, where you can put this anywhere on your machine. I just wanted to put it in my downloads for whatever reason. And star.uf2 should see these three files exactly. ls home Bryson downloads. Perfect. Okay. And so now what I'm going to do is quit that. Is now all I have to do is open this up, go to my downloads folder, and I'm ready to roll. So what I'm going to do now is I'm going to load each of these subsequently onto the respective and appropriate corresponding Raspberry Pi Pico microcontroller on the Neuromorphic Maker Skit. Okay, back to our hardware setup now. So as you can see here, we have our window open on our machine that now has our .uf2 binary files I'm highlighting right now, these three files that we want. Once again, we want to get each of these files onto the respective device, on the respective Raspberry Pi Pico on the Neuromorphic Makers Kit. So to do that, we're going to take our micro USB cable, see micro USB in there, and then we're going to take the in that we want to plug into our laptop with whatever that is, in my case USB-A, and we're going to be plugging that into our laptop, desktop, whatever local device you have here, single board computer, wherever you want. Wherever you have your .uf2 files stored now for the binary decimal application. And so the way that we're going to be loading code onto these Raspberry Pi Picos is pretty simple. We do not want to have power applied already. And what we're going to be doing is, see, there are these white little switches, push button switches, on all of the Raspberry Pi Picos, and it'll probably be labeled boot cell, BOOTSEL, and that stands for boot select. And what that allows you to do is while you press down a switch and apply power, once again, if power is not already applied, say with this barrel jack, then it will open up in boot select mode, the Raspberry Pi Pico microcontroller will. And what that allows you to do is you can then just drag and drop from the computer that you have connected to it your .uf2 file to the Raspberry Pi Pico device, to the microcontroller device, and it will load that .uf2 file, that binary compiled code, onto the device and automatically start running it. And it'll start running it every time you reapply power after that because it gets stored in some non-volatile memory. And so it's very nice. So basically, boot select mode is an easy mode to load encode. And so once again, you cannot already have power applied, so make sure it's not plugged in this example. And then press down the button. We'll start in this case with a spike encoder, and then plug in your micro USB cable. And as you can see on the right here, it came up with this RPI-RP2 device. This device is it shows up as a drive in Ubuntu here. And on this drive, we're just going to drag and drop our desired.uf2 file. So, and once again, it's on the Neuromorphic Makers Kit. It does have spike encoder labeled and the spike decoder labeled on the PCB where my finger is pointing. And so because of that, you know which one's the spike encoder, which one's the spike decoder, and which is the right Pico to load the code. And the one not labeled is the neuroprocessor, in our case RISP, where we'll be loading the RISP.uf2 file. So I just plugged in the spike encoder, and so that means I just drag this spike encoder.uf2 file highlighted right here to the RPI-RP2 drive that showed up whenever I plugged in boot select mode the Pico. So I just do that. And notice it disappears and injects the drive. And what this means is right now it's actually running our Neuromorphic Makers Kit binary to decimal code on here. That's not very useful since we need all these powered on and running the right code at the same time to actually do anything. So we're good to go. But now anytime I reapply power, so for example, power off because I unplugged it, power on, it is running once again that code. You don't have to press boot select and do that every single time. Anytime you apply power, say by, for example, plugging in the Neuromorphic Makers Kit, it'll start running the code on all the Raspberry Pi Picos that's loaded on there at once, which is exactly what we want. So just repeat the process for the remaining Raspberry Pi Picos. Press boot select, insert the micro USB cable. Once again, it comes up with the drive RPI-RP2. This is the middle one, so this is going to be RISC.UF2. I think I missed it there. Drag and drop. And documents. Yeah, my mouse isn't the best here. So that's why it's doing this. I accidentally clicked on the wrong thing. So I need to go back to downloads. There we go. Just in case I didn't get it there, I'll try it one more time. Since my mouse accidentally let go of it while I was dragging and dropping it. RISC.UF2, highlight it, drag it over, and it ejects it. So now we know we're good to go. And repeat for the final Pico. Press down the boot select button, plug in the micro USB cable, make sure spike the right .uf2 files selected. In this case, spike decoder.uf2. Happen again. There we go. Spike decoder.uf2. Drag and drop. It'll eject. Code's running. And now it'll run every time we plug it in. So now we're good to go. Everything's loaded on. Code's loaded on. Hardware is all set up. All we have left to do is I'm going to turn on my power strip here. Plug in the barrel jack, and then plug in the barrel jack into the Neuromorphic Makers Kit. This is it. This is our application. We are completely done. All that's left to do is to test it. So 3 buttons. Each button represents a bit out of the 3 possible input bits. And so it will convert the 3 bits into a decimal number. That's what the spiking neural network does. And then it will blink on the spike decoder that I'm pointing at here. There's an LED where my finger is that you'll notice once it starts blinking. That LED will blink the correct number of times for the corresponding output decimal number. So if you want to figure out which one's the most significant bit, the easiest way of doing that is just testing it. So like here, I'll press one end. Oh, that blinked 4 times. So I know it's the most significant bit. And let me try the opposite LED. That one blinked just once. Okay, so now I know that this LED is the least significant bit, and then, this button represents the most significant bit, and this button represents the most significant bit. Sorry, this button represents the least significant bit, and this button represents the most significant bit. And then the one in the middle is the bit in the middle. So now I will show you that this works. So I will press the button for 1, and you'll see that the LED on the decoder lit up once. 1. I'll press it again. 1. I'll press it again. 1. It's decoding the binary number 1 into the decimal number 1, and it blinks 1 time on the output. Okay, now I'm going to do the same thing, but for 2. So I'm going to press just the middle button. 1, 2. See the LED blink. 1, 2. And then same thing for 3. So I press the first 2 bits simultaneously, the 2 least significant bits simultaneously. 1, 2, 3. 1, 2, 3. 1, 2. Bad timing on that one. 1, 2, 3. There we go. Now I'll press 4. 1, 2, 3, 4 blinking. And then 5. 1, 2, 3, 4. Oh, I didn't. Once again, the timing's a little jittery on this. You have to make sure you press them down about at the same time. 2, 3, 4, 5. There we go. And now we'll do 6. 1, 2, 3, 4, 5, 6. And now we'll do 7. 1, 2, 3, 4, 5. Oh, I'm once again bad timing on my part. 1, 2, 3, 4, 5, 6, 7. There we go. Okay. So this is your binary decimal application. You can play around with it as you see fit. You'll see that the as I showed, especially in this example, it didn't blink the right number of times I wanted to because you do have to press down the button simultaneously, and it has to be pretty close to simultaneous. The timing tolerances that's in the input code and the observations code and the actions code that I mentioned earlier in the software portion is only so sensitive to timing, and so because of that, you have to make sure that you press it down roughly at the same time, but as you press around with the buttons and mess with it, you'll get a good feel for it. 1, there's 6. Yep. Okay. So if you have any questions, first consult the documentation, the readme.md file inside of the software repository that I showed you all. But if you still have questions, comments, concerns, feel free to email me at my email address that is also inside of that documentation. bgl1@vols.utka.edu. Consult the README for that. But okay, anyway, thank you.